Okay, the next type of, the last form of equations are equations that require an integrating factor. So that's the last part, integrating factor. Let me see if you can see this. Let me get a better pen, sorry about that. Let's try another pen. Let's see, let's try this one. Okay, the form is dy over dx plus a function of x times the constant y is equal to another function of x. That's the form. What you're going to do is you're going to take, when you see it like this, you can choose the other three. If you can solve it, if you can get x and y alone, go for it. If you see a y over x, go for the second method. This is a much easier method, and once again, this is just your intro to differential equations. So like, they're not going to be difficult, and they're going to work out nicely. Okay, so we have the form dy dx plus p of x times y equals q of x. What you're going to do is you're going to take the p of x, you're going to take this term, and you're going to recreate a function called the integrating factor. Integrating factor. Okay, I of x is going to be equal to e raised to the integral of p of x dx. Don't worry, it's going to be easy to do. Okay. Then what you're going to do is you're going to multiply each term by I of x. Okay. Now, what's going to happen is it's going to work out really nice. Okay, because it's going to turn out that you're going to look at the left, and you're going to be able to rewrite it as d dx of the integrating factor times y. This seems a little confusing, but it's going to work out. Can you see that? Yeah. And then what you're going to do is you're then going to integrate both sides. Integrate both sides. And then you're going to solve for y. Once again, this is your first time seeing differential equations, and you're just high school kids. So it's going to be very straightforward. And they're probably going to tell you that, they're going to tell you, like, what the integrating factor, they're going to guide you along. Okay, let's do an example. Let's do something very basic. Let's see. The first example is, whoops, sorry about that. So, the first example we're going to do is, let's do it over here. Okay. The first example is dy over dx plus 2xy equals x. Good. Okay. So first of all, it's in the form of the way we're going to use the integrating factor. Some of you might say, "Hey, Mr. Adler, I can do this on my own. I can factor out, an x. Let's use the integrating factor for today. So, I of x is equal to e to the integral of 2x dx, which is equal to e x squared. Step 1. Step 2, multiply everything by the integrating factor. So we have e to the x squared dy dx plus e to the x squared dxy equals e to the x squared times x. Now, it's not a coincidence. You might be saying, hey, you know what? The derivative of e to the x squared is e to the x squared times 2x. So we notice it's d dx times e to the x squared times y. you can recognize that, or you can just say, you know what? The rule is it becomes the derivative. It's like you're reversing this. You know, how did you get this whole thing? You go, oh wait, I took the derivative of the integrating factor times y, and that's equal to e to the x squared times x. Now you say, well, that's a little confusing. It's not confusing. Next, last step, take the integrals of both sides. Wow, this is nice because an integral undoes the derivative. That was a theory that I taught in the old option. They don't teach it anymore, but it's like they're inverse functions, the integration and the derivative. So we simply have e to the x squared times y. What's going on over here? Well, this is dx. This works out nicely because if I have to take a u substitution, du over 2x equals dx, right? And so you have the integral of e to the u x over 2x du. This is equal to 1/2 e to the u du, or final answer, so we have e to the x squared y is equal to 1/2 e to the x squared plus c. Final answer, y is equal to 1/2 plus c e to the negative x squared. It's tedious. Once again, as I keep saying this, it's tedious. It's not difficult. There is nothing here that you can't do. Let's look for another example. Let's look at the next example. Right? The next example, am I recording? Yes. The next example is dy over dx plus 3x squared y equals 6x squared. You might say again, you know what, I can solve for x squared. That's fine. Let's use the integrating factor method. It's in the form dy dx, p of x times y equals q of x. Fine. So we know that I of x is equal to the integral, it's equal to e to the integral of 3x squared dx, right? Which is equal to e to the x cubed. It's not a coincidence that this all ties in together. The derivative of e to the x cubed is e to the x cubed times 3x squared. That's going to be nice when we multiply everything through. E to the x cubed dy dx plus e to the x cubed times 3x squared y equals 3e to the x cubed times 6x squared. This is not a coincidence. Some of you are saying, oh, hey, Mr. Elder, when I take the integral and you do that u substitution, that 3x cubed, the derivative, when I take the derivative and put it in the denominator, it's going to knock this out. Not a coincidence. Like, that's what you're looking for. Okay. So, what's going on here? Well, we know the rule is it's the integrating factor times y, and that's equal to e to the x cubed 6x squared. Cool. Next rule, take the integral of both sides. Okay. Well, this works out nicely because the integral and the derivative are like inverse functions. It's a little more advanced than that. You'll go over it in more abstract classes in college, but we don't cover it here anymore. You can in the option books if you want to see it. Anyway, we have ex cubed times y is equal to, what's going on over here? Well, I'm going to take it off to the side. I know that u is equal to x cubed. Therefore, du over 3x squared equals dx. So I know it's the integral of e to the u, right, times 2 du. Please practice this. So let me go step by step. you have to pick up the pace a little bit, right? So this becomes the integral of e to the u 6x squared times du over 3x squared. That goes out with that. We're left with 2 du. So we have e to the x cubed y equals 2 e to the u plus c. E to the x cubed y equals 2e to the x cubed plus c. Final answer, y equals 2 plus e to the negative x cubed. Once again, it's a little tedious. This is probably the tedious part, but get your integration down. And you'll practice these examples. Let's try another example. Let's try something that looks like a previous problem. We'll do it over here. Let's try this one. I found it in the book. dy over dx plus 3yx equals e to the x over x cubed. You might say, oh, can we use the y over x? Maybe, but the problem is going to probably tell you to use the integrating factor. Okay, what's the integrating factor here? Okay, well, I know I of x is equal to e to the integral of 3 over x dx, which is equal to e 3 ln of x, which actually is equal to, I want you to figure this out on your own, it's actually x cubed. Think about that. Well, this works out nicely. Let's multiply everything by x cubed. So we have x cubed dy over dx plus, what do we have here? We have 3 over x, y times x cubed, equals e to the x. Let's clean this up a little bit. Well, it's x cubed dy over dx plus 3x squared y equals e to the x. Now this works out nicely. These problems come together. The next one's going to be a little weird, but, well, no, it's not. These problems work out nicely. Well, this is clearly d of x cubed y, which is equal to e to the x. Take the integral of both sides. So we have x cubed times y equals x squared plus c. Please don't forget the c. Do not forget the c. Unless you got a boundary condition at this point, this is where you apply it. So once again, apply boundary condition. Sorry, I'm racing. Boundary condition here. Same thing, right here you'd apply your boundary condition. The second the c appears, that's where you stick it in. If there is one, I didn't give you one. Final answer, y equals x e to the x plus c over x cubed. And last, let's do the last problem. This one's a good one. I like it because it just throws everything together. These are really great methods of practicing all your integration. Now, for those of you who are thinking about taking engineering in college and physics, they make you sit through differential equations. You have to take these classes. So let's try this one. Ready? Ready? Who's ready? Cosine of x dy dx equals y sine of x plus sine of 2x. So you look at that one and you're like, what is going on here? You know you have a differential. You're trying to solve for y. You can't make head or tails of it. Well, you kind of do have it. So first of all, get dy dx alone. So let's divide everything by cosine. So we have dy over dx is equal to y tangent of theta of x plus sine of 2x over cosine of x. Can we simplify this actually? Is that sine of x? This is, yeah, What can we do here? Well, this is 2 sine cosine. So that's 2 sine, right? Once again, sine of 2x is 2 sine theta, 2 sine x, cosine x, divided by cosine. This is equal to 2 sine. Okay, so, and if you say, oh, wait a minute, this looks like the integrating factor form. So let me pull this over here. So I have dy over dx minus y tangent of x equals 2 sine of x. Okay, nice. First of all, what is my integrating factor? The integrating factor is the whole thing in front of the y, which means this negative. That's what goes in the exponent. Please remember the negative. Don't forget the negative. That's going to ruin the whole problem if you don't. Fine. We know the integrating factor is equal to e to the integral. I'm going to pull the negative out of tangent of x dx. Okay, I got to figure this out. We did this before. You've practiced it. Maybe it's in your formula booklet. Why don't you pause your video and see if it's in there? Okay, you're back. Let's just take the integral. Well, I know that the integral of tangent, that's equal to negative integral sine over cosine dx. Okay, let me let u equal cosine of x. That means du over negative sine of x is equal to dx, which means we have the integral of negative integral sine over cosine over u times du over negative sine of x. This is tedious, but it's a good problem. It brings everything. The negative goes out with the negative. The sine goes out with the sine. We have 1 over u. Well, what's the integral of 1 over u? Ln of, what was it? Ln of cosine of x. Well, that's really convenient for us because this is e to the ln of cosine of x, which is equal to cosine of x. That works out really nice for us. Okay. Right? Does everyone see that? We figured this out. Like 1, 2, 3, 4, 5, and now 6. Okay. Next step. Let's multiply everything by the integrating factor. So, let's see. We have cosine of x dy over dx minus y tangent of x cosine of x equals cosine of x sine of x. Now, this works out nicely because, let's just fix this up a little bit. Let's fix this up because I want to make my goal is to make my life easier, right? I don't want to deal with the sine and cosine, so hold on a second. We have cosine of x dy over dx minus, well, tangent is sine over cosine, so this is y minus sine of x. Please remember, tangent times cosine is sine. And this is equal to, ready? 1/2 sine of 2x. Maybe I should have just left that. Maybe I shouldn't have even bothered, right? 2. Oh, I forgot the 2, right? 2. There should be a 2 here. Oh, this works out very nice. Oh, nice. Once again, excuse my mistake. There was a 2 up here, right? 2. 2. Nice. Perfect. Well, what's the rule down here? Let's see. This becomes the integral of... no. Sorry. This becomes d dx of the integrating factor cosine theta times cosine x times y, which is equal to sine of 2x. Let me erase this over here. what's going on over here? So we're going to take the, okay. What we're going to do is we're going to take the integral of both sides. So we have cosine of x, y is equal to, what's going on over there? Well, we know it's 1/2 cosine of 2x, but it's negative because remember the integral of cosine goes to negative cosine. We remember the whole u substitution, so that 2 is going in the denominator, and we have the plus c, right? And then a final answer. What is the final answer? That's it. Y is equal to 1/2 cosine 2x plus c all over cosine of x. You'll notice in the book that they actually, at this point, they give you a boundary condition. So I think c ends up being 3 and the 2 goes in the denominator, but that's okay. The idea is this is the answer. So work on the problems in the book. Practice as much as you can. This is like just endless integration. Good.